Now to your talk on algorithms for robust query processing, which will substantiate this claim. All right, thank you.
Thank you, Nildara.
I think we should welcome Vinayaka.
Okay, I thank the organizers for giving me this opportunity to present this work here. So this is joint work with a bunch of people from IISc, Professor Jayant Haritsa, his PhD student Srinivas Karthik, and master student Sanket Purandhare, and couple of people, my colleagues at IBM Research, Lohit Krishnan and Shreyas, but Shreyas has since then moved to Walmart Labs. So incidentally, so Jayant is giving the same talk in Kolkata today. So those of you who have been to Jayant's talk would wish that you would rather be in Kolkata than here, but you have to bear with me. So I think this talk requires a bit of background on database query processing, and also a little bit of background on what work existed before we did our work. So I'll not assume that you know any of those things. So I'll kind of give you very gentle introduction to query processing, and also what these Bouquet algorithms are before I kind of get into what we have actually done. So I'll not get into too much technical details of what we have done, just the main ideas. I think as long as you kind of get the definition of what the problem is and what are the results that we have got, I think I would have achieved my objective for the talk. Okay, so a little bit about the title. So query processing is, I think, clear to everyone. So database work by people submit queries, and you have a query processor which processes the queries. The robustness here refers to how robust is your query processing engine to errors that it makes in certain estimations that it works with. And Bouquet algorithms, the Bouquet actually refers to a bouquet of plans that we are going to work with. So I'll be introducing all these concepts to you. Okay. So every organization has fairly large databases running, and for last 3 decades or so. So one would be tempted to ask, why are we still talking about query optimization? Isn't it a a well solved problem? I kind of resort to proof by authority here. So Guy Lohmann is actually an authority in database query optimization, one of the key architects of the DB2 query processor. So he has been writing of late, about, is this a solved problem? Right? So people had kind of stopped working on this problem. So he's kind of been highlighting that this is not really a solved problem. Forget from a theoretical point of view, from a practical point of view. He gives many interesting stories of real database deployments, wherein people have horror stories of queries that they were expecting would run in minutes, but it actually takes a few days, right? And there are instances that he talks about where you have a database query that is taking a few hours to run, and so you feel that, okay, let me rewrite this query to help the query processor. You rewrite it, and when you rewrite it, instead of hours, it takes days. Okay, so it's a very poorly understood problem. So even people who try to optimize queries based on how it is behaving do not really understand what the query optimizer is doing inside, and hence they are always in for surprises, right? So that's proof by authority. And other is actually this very interesting work by people Leis and others from Technical University of Munich. So what they have been doing is they have been looking at characterizing how good are these query optimizers, right? So what they have done is that they have explicitly constructed what we call as hardnut cases for query optimization. Okay, so these are hand constructed benchmark that they have come up with, which are difficult for query optimizers to do well on. Okay, and what they have seen is that certain estimates, we will talk about what those estimates are, certain estimates that the query engines work with, the multiplicative error, right, is of the order of 10 to the 4, huge estimation errors are there. And because of that, what you see is that the optimizers can be, they have seen many instances where the optimizer is 800 times slower than what the actual optimal plan would have been if you actually had the correct estimates. Okay. And so in the last 8 years, so there have been several dark stool seminars focusing on this particular problem. Okay. So for the next few charts, what I am going to do is I am going to take one example query and kind of introduce all the concepts to you with respect to that. So this is a schema diagram for a database from manufacturing sector. So basically, each box here is a relational table, and a directed edge says that from the source table there is a foreign key in the source table which refers to a primary key in the target table. Okay. And let's consider a simple query. So it basically says that I want all the details of orders for cheap parts. Let's say those parts which cost less than $1,000. Right. So this is what you want, and what you will do is that you will write an SQL query which looks like this: select star from these three tables where the price of the part is less than 1,000, and in these two tables these keys match, so that you are giving the full details of what those orders for the cheap parts are. Okay. So I hope people are familiar with the operators for relational database execution. So so here is one plan, right? So plan is basically a tree of operations that is going to take place, with the actual base tables being at the bottom and the final answer being at the top of this particular tree. So here is you will take the parts relation and you will do a select operation with retail price, and then you will join that with the table line item, and then you will join the result of this particular operation with the orders table, and then what you get as the output of this join is actually the answer to your query, right? But the thing is, this is not the only way you can actually execute this query. There's another way, right? So you could, instead of joining the select output of the parts with line item, what you could do is you could do a join of the orders in the line item table, and then join it with the output of the select operation from the parts table. Okay. So the heart of the query optimizer is that given a query, which this is actually a very simple query, but if you look at the queries that are there in the TPCDS benchmark, which is actually a benchmark of queries to evaluate how good database query engines are, these are very complex queries. Okay, so if you think of these joins as predicates, and the select operation also as a predicate, it has only 3 predicates. TPCDS benchmark has queries which are in excess of 10 predicates. Okay, so the plan will look fairly deep, and hence the number of semantically equivalent plans is like really large. And then this is not the full story. Even if you have a plan like this, what the query optimizer also has to do is, for each one of these operations like the select and join and so on, there are several alternative implementations of each of these operators. You can do join in many ways, you can do a scan, or like even a select operation in many ways. Okay, so there are multiple implementations of each of these operators. So the query optimization engine, what it needs to do is it needs to come up with the plan that it is going to execute, and also at each of these operators it needs to say what is the implementation of the operator that I am going to use for executing this particular query. Okay, and all of this it does basically based on some sense of what is the cost for each of these operators. Okay, and then the costs are going to add up. Most of the time people use the response time, which is the amount of time that the query is going to run in the system, as a measure of cost, but you can have other measures, right? So in a heavily power constrained kind of application, you may have power as a cost measure, and in certain cases where communication is involved, you may have how much bandwidth you are using as a measure, but typically response time is the measure that you work with. Okay. So the reason why databases are very popular is that they give you a very simple abstraction for the programmers, right? So the programmers, as you saw, they write a very simple SQL query which just focuses on what is it that they want from the database, right? They don't say how you want it, how it should actually get the results for them. That's the job that the query optimizer does. It gives you the optimal plan, right? That's why there are a large number of programmers who don't have to worry anything about how query optimization works. They can just write these declarative queries. So there are two kinds of models that query optimizer works with. First one is actually what is the kind of hardware on which it is running. For example, most of the databases have the relations stored in the disk, and so there is the cost of bringing pages from the disk to the main memory and so on, what is the cache performance, etc. So all of that hardware characteristic of the platform on which the engine is going to run, that is, they make a model of it. It's basically called just the operator execution cost model. Okay, so that is one input to the query optimizer. Second is the what we call as the cardinality estimation or the selectivity estimation, which is going to be the focus of this talk. Okay, so both of them, errors in both of these things have an impact on the query optimizer, and I'll tell you in a bit what the impact of this story. Question?
So when you say it's an optimal plan, is there like a certificate of optimality?
No. So people who work with databases, they assume that it actually gives an optimal plan. So the claim, as I said in the introduction, is that it is far from optimal. It is optimal if each of these inputs that it takes are accurate. Okay, but the problem is that these are mostly not accurate. I'll come to that. Okay. Yes. Yes, optimality includes that also. Yes. Okay. So one thing we need to kind of understand is this notion of selectivity for me to tell what are these models being accurate means, right? So the key thing is this notion of the selectivity. Okay. So as I said, there are these operators, and each of these operators, they get certain inputs and they are producing some output. Okay, and the selectivity of that particular operator is basically the ratio of actual number of tuples it is going to output versus what it could have produced in the worst case. Okay, so for example, in the join operation there, right? So it can potentially produce an output which is the size of the relation on the right hand side. Okay, but it has only produced half of that. In that case, the selectivity of that operator is said to be half. Okay. So in this example here, you started with a parts table which had these many rows, and it only produced that many rows. Okay, so the selectivity of that is 0.2, because it could have potentially produced all these rows, but it only produced a small subset. Now similarly, the join also, as I said, it could have produced that larger table, but it actually produced half of that table. So the selectivity is half. So now, why is this important? So this is important because, as I told you, the query optimizer has to decide which implementation to place here, which implementation to place there, which implementation to place here. Okay, so this estimation, which says that, okay, what is the, for example, for the hash join, right? What is the relative size of the two relations that are coming into it? Is one of the factors that determines what implementation you are going to use there. Hash join is one particular implementation. You could use a nested loop or many other. There are 4 or 5 different things. So that is the decision. That decision as to which implementation you are going to pick there depends on what do you assume is the selectivity that is coming in, selectivity of this downstream upstream operators, which in turn implies how many tuples are going to come, which determines what operator you are going to place. Okay, so that's why this selectivity is very, very important. Okay, so so when you give a query, what the database query optimizer does is first it comes up with this kind of a plan. It comes up with many alternative plans, and then for each one of these alternative plans, it comes up with what could be the selectivity at each one of these nodes. Okay, and based on that, then it figures out what is the appropriate operators, like the implementations that you want to place in each one of these nodes, and that determines the performance of the query optimizer. Okay, so these are the things that it is trying to estimate. And typically where they can do well is these are called base tables, which are essentially the actual tables. If you have a select operation on a table like this, you can do reasonably well, because you can maintain histogram of that values of let's say the primary key and or even important columns and so on. But these intermediate results, right, the selectivity estimations for them, that is actually the harder problem. Okay, because in the previous, even to process that particular claim, that query, this operator will go to another hash join. So if this is off, everything is off. No, that's not helpful actually. So yeah, so sampling, I mean, I'll not go into it, but sampling has so far not helped in the case of query. Okay, so so because of this estimation errors, you get suboptimality, right? So one is there is this cost model, which I talked about, which is basically a function of what kind of hardware features it has, what is the exact design of the database engine, etc. This has a very limited impact, okay, about 30% impact on your performance. Could be 30% off from what you estimated it to be, okay. But the bigger impact is in the cardinality errors, okay. Here, if you make mistakes here, you get huge impact, and this is what that particular work that I talked about from Munich, which showed that the estimation errors in this cardinality estimation actually resulted in slowdowns of up to 800 times, okay. And like if you really want to construct very bad examples, you can even make it like million times, etc. But this is on realistic database benchmarks that they have done. And there are various reasons. I'll not kind of get into it. This is like very database literature specific comments, right? So just to kind of give an example of what this error is, right? So when you get the query, this is the query you gave to the optimizer. It does not know anything other than maybe it maintains some base statistics about this line item table, parts table, and orders table, right? What it does is it can make certain assumptions. So one assumption it can make is that, let's say, it assumes that orders for all the prices are equally likely. Okay, let's say it makes that assumption because it let's say it has outdated statistics on the orders table. Okay, so then based on that, it comes up with certain estimation of what is the number of rows that comes out of each of these intermediate nodes, and then it has come up with an estimate of how much is the expected output. It assumes that roughly 10 to the 3 records are going to come out of the result for this query. Okay, but what can happen is, suppose you have an instance in which there is only one cheap part, then the optimal plan actually looks very different from that plan, okay, because it does not make sense for you to kind of do sequential scan of any of these inputs, because that there is only one cheap order for one cheap part, or you could be it could be way off because let's say all the orders are actually for cheap parts. in which case you would actually do sequential scan. You will not do index scan anywhere, because you know that you have to look at every row of every table, right. So the optimal plans looks very different from the actual plan. Okay. So this is the impact of what happens at the compile time and what happens at the runtime when a query comes and when you are trying to execute it. I will not spend much time here. People have been conscious of the impact of these estimation errors, and the database literature has been actually trying to address this problem for last 2 decades. But the main thing is that most of this work actually does not look at it from a worst case point of view. Does not look at what is the worst case performance hit that I may take because of the approach that I take, right. So the first work is actually the work that Professor Jayant Harisa and his student Anshuman Dutt did in 2014. The algorithm is called the PlanBouquet algorithm. So they came up with a formulation of a particular robustness metric called maximum sub-optimality, which I will talk about, and they showed that there is one algorithm which gives a reasonable bound on the worst case performance hit that a query engine can take if it follows the PlanBouquet algorithm. Okay. So I will kind of talk about this algorithm a little bit, because you need to know what this does before I tell you what we have done, and it also introduces some of the important machinery. But just in case I don't get to the part that about the work that we did, so our work basically builds on Jayant's earlier work, and what we show is that we give an alternative algorithm and alternate bound which has certain better properties than PlanBouquet. I will talk about it later on. And then we also showed lower bound on any deterministic algorithm for processing, like for robust query processing, and another improved upper bound for that particular problem. Okay. This is all in the execution phase. Okay. So I showed you that there are 2 phases. There is a compilation phase and there is a execution phase, but the PlanBouquet algorithms suffered from the fact that the effort at the compilation phase was just too much. I will tell you how bad it is. Now that was actually a big problem for database community to adopt it. Okay. In a recent work, what we have done is we have shown how you can actually get the same bound as what we have, but with completely eliminating the compilation phase overhead. Okay. So this is like the landscape of the entire work, and D here will always refer to the number of predicates in the query that for which the estimation is difficult, or for which you are not confident of the estimation that you are going to come up with. Okay. So again, coming back to this particular query, so let's say that there are these 2 hash joins which we call as predicates x and y. The selectivity of these 2 is, let's say, difficult for us. We don't know how to do it. So the first thing we define is what we call as an error prone selectivity space. It is just if there are d predicates, it's a d-dimensional grid with all the selectivities varying from 0 to 1. Okay. So it's a normalized selectivity 0 to 1, and a particular query basically is represented by a point in this. Okay. So if x and y had 0.4 and 0.3, that would be the query point actually for us. Okay. And q's will always represent locations in this particular space, and p's will always represent plans. Okay. So cost of pq is, if you take a particular plan p and you execute it on an instance where the actual selectivities is at q, then that is the cost that you are going to get. and P's of Q will refer to the actual optimal plan that you would pick if you actually knew Q. Okay. So typically if you model, let us say the existing database engines, the way the situation looks is as follows, right. So QA is your actual selectivity for the instance, okay, and QE is what the database engine thinks is the selectivity. Okay. So what it is going to do is at QE it is going to pick the optimal plan P of QE, right, whereas it should have actually picked P of QA, and then what it is going to do is it is going to execute the plan using P of QE, right. So the cost it is going to incur is cost of P QE at QA, whereas it should have incurred a cost of P QA at QA. Okay. So this is the suboptimality if you picked QE as the estimate for the actual query location QA. Okay. So maximum suboptimality is over all potential pairs of QE and QA. What is this quantity? Is this clear? Just the worst case suboptimality that you can get because of erroneous estimate of the selectivity. Okay. And this is the quantity that we want to kind of get a bound on. Okay. Now the query processing algorithms that I am going to describe, they are not going to evaluate one plans, they are going to evaluate multiple plans, okay, and they are going to explore multiple locations also. For example, it may think that Q1 is actually, it will begin with asking the question, is Q1 the location, and at some point it figures out that Q1 is not the location, it makes a hypothesis, it says okay, maybe Q2 is the location, and so on. Finally it comes up with an estimate which is, let us say, Q final, which spatially dominates the actual query location, and the plan you pick there is actually going to run to completion. Okay. So the same thing I have just written here, except that previously I had just written the cost for that QE. Now instead of that, what you will do is you will add the cost that you incur at each step of the way. Okay. So if you went from Q1 to Q final, and let us say that at each of these steps you picked some plan P of QI, which is the optimal plan at that particular estimated location, and you gave it a budget saying that okay, run this plan with this much budget. Okay. If you finish, good. If you do not finish, I am going to terminate it and go for another location. Okay. So for at each step you are giving, incurring that much budget, so you are just adding up that budget. Okay. So assumptions, a very simple assumption, and this standard one in database literature is called Plan Cost Monotonicity, which just says that if there are 2 points Q1 and Q2, and let us say Q2 actually dominates Q1, then the cost of a plan, you pick any plan, you run that plan when the actual location is Q1, then that cost is going to be less than running the same plan P on another instance where the actual location lies at Q2. Okay. It is a very simple, and it is a standard thing. For simplicity of proofs, we also assume that the cost model of the hardware and the system is perfect, but this is not essential. We can do away with this, but we assume that this is perfect. Okay. So what happens at the compilation phase is, so again I am just showing you with just 2 predicates, and I can't recognize all the colors, I am color blind. But this is actually, these are nice pictures that there is a tool in Jain's lab called Picasso. They do not look like the pictures by Picasso, but it's his take on what he thinks of Picasso as a painter. So what it does is, this is the space in which you are trying to estimate the selectivity. For each one of these location, it takes the optimal plan. Okay, and it gives it a color. So every region with a particular color, That is, the same plan is optimal in all those regions, okay, and that is the cost it is going to take, this particular axis, and then you do it all the way up to the last location where the selectivity is 1 for every dimension, okay. And then what you do is that let us say C max your highest cost, then you kind of take half, at every step you take the half of that particular cost, and you cut it with a plane of value C max by 2 to the I, and then whatever plans you get, that is actually called this is the top view you get, and that is the set of plans we are going to work with. So essentially this is all the plans that incur maximum cost. This is all the costs, all the plans which incur half that cost. This is 1/4 of that cost, etc. And in each one of those contours you have different plans that are there, okay. And this is the bouquet of plans that we are going to consider, okay. So this is we will not look at any other plans. As you can see, at each point in this location there are optimal plans sitting, but we will not consider those, we will only consider these. But to come up with this, we actually had to compute the optimal plan at each one of these things, and this is actually one of the biggest drawbacks of the PlanBouquet algorithm, right. If you have a d-dimensional error selectivity space, you are calling the query optimizer on those many points to asking it, okay, what is the optimal plan here, etc., and that is one of the drawbacks, okay. But this picture is clear, right. So it's these are the selectivities on both the axes. These are the isocost contours. At every step it is doubling except the last one, and in each contour there are multiple plans, okay. So those are the optimal plans in those regions. And so this rho is a quantity which is going to come up in the bounds. So this is, if you look at a contour, what is the maximum number of plans, that is, okay. Now just to give you an idea of what is going on here, we will consider a very simple case where there is only one error prone predicate, okay. So there is only one, it can go from 0 to 1, right. So then so there is, let us say C is the minimum cost that you incur for any selectivity, and then you have these plans at every doubling cost, right. And let us say that here QA is your actual query location, right. So what I am going to do is I am going to pick the least cost plan and I am going to run that, okay. I will run it only till it incurs a cost of C, okay. And once it incurs a cost of C, I know that this is not the actual query location. I am going to stop it and I am going to jump to the next plan which has a cost 2C. So this is my estimate of the location now, and I will pick this particular optimal plan and I will run it till I incur a cost of 2C, okay. Again I will not terminate because the actual query location is still far away, and so on, and finally when I go to P4, right, I will definitely terminate because I am giving it enough budget, right. And because of the plan cost monotonicity, if this plan takes 8C here, it is definitely going to take less than or equal to 8C here, okay. So that is where the plan cost monotonicity assumption comes into picture. And now for us in theory this is fairly simple. This is a 4 approximation to the maximum suboptimality, right. So this would have anyway incurred at least 4C, and you have incurred at most 8C plus 7C, right. So this is actually what PlanBouquet did, okay. So it showed that now in D dimension all you do is you go to every contour and you execute every plan in that contour with that much amount of budget, right. So the same analysis carries through, except that at each of these contours now, instead of 2 to the I times the minimum cost, you are incurring at most rho times 2 to the I of that cost, and hence the ratio is 4 times rho, okay. So this is where the previous work was, but the biggest drawback it had was that if you had a grid with d predicates, and even if you want some granularity of, let's say, r, resolution of r points on between 0 to 1, then it actually required to make r to the d calls to the query optimizer. Okay. So that's why we could do, they could do, and even in our first work we could do experiments only up to d is equal to 5, because beyond that just the compilation phase was taking too long. Okay. So this is one problem. The other problem is this rho, which is actually the number of plans on the cost contour. That is actually not a function of the query, but it's actually a function of the engine that you are using. If you go from one engine to another engine, this rho can easily change, because the engines work very, very differently. And it also, I'll gloss over that particular point, it makes use of a particular heuristic in database literature, which is called anorexic reduction, which says that that particular picture that I showed, the Picasso picture, so if you just actually did the simplest one, like you just every point you take the optimal plan, that will have far too many colors. Okay. So the anorexic reduction says that you can actually subsume some of these colors with plans of other colors without losing too much cost. And experimentally what they have seen is that without blowing up the cost by more than 20%, you can actually bring down this number of plans, number of colors to a small number. So that's still an assumption. So it assumes these two things. We wanted to move away from that. And finally, we have also been able to address this issue of huge compilation effort. Okay. So I don't know how much time do I have? Okay, then I'll just try to wrap up quickly. So what we do is we don't the PlanBouquet algorithm actually treated the query optimizer as a black box. Okay. Instead, what we do is we do some surgery into the query optimizer. It's a very minimal surgery. It's just about like if you want an extent of it, in the entire Postgres query optimizer, we add about 100 lines of code in a particular place to get certain information. Okay. And what we do is we call it as spilling. What it does is, I told you about this operator cost estimation, right? So for the entire plan, it has come up with a particular cost. What we do is that, let's say we are focusing on what to discover this particular selectivity, right? Then we want to use that cost maximally for just this purpose and not do anything for this particular operator. What we do is we cut off here and we call it as spilling. Okay. So we cut this off and use the entire budget only for this part of the tree. We don't evaluate this part of the tree at all. Okay, it gives us a particular benefit. I'll tell you what it is, but that is actually the critical thing we do. Okay, so we spill it and we focus on a particular dimension and we try to learn its selectivity in an appropriate manner, which is not possible in PlanBouquet. Okay. So this is what it is showing. So instead of using that budget for the entire tree, we just use it for this particular subtree. Okay, and we always pick the one in that subtree, whichever predicate we pick, that will be the first predicate with which is prone to selectivity error estimation. Okay. So I'll just show you by picture. So what it does, what it gives us is the following. The PlanBouquet, when it ran this particular plan P at this particular location, and if it does not terminate, all it can conclude is that the query location does not lie in this region. Okay. But what spilling allows us to do is, without going into details, is that it allows us to rule out this entire region. And this is a big benefit. I'll tell you why. Okay. Okay. The reason is that now what I can do is that this is a picture for 2 dimensions. So there are so many plans, right? So and PlanBouquet was actually evaluating all these 7 plans. Okay. What we do instead is we look at each of these plans and look at which predicate it is spilling on, okay, which is the nearest predicate for which I can spill on, and I annotate it by that. Okay. On the x dimension, I will pick the plan which has the highest, which has a x here and which is the the rightmost, and here which is y and which is the y most. Okay. Now the claim is that if I just execute P3 and P5, it is sufficient for me to rule out this entire contour. In fact, it allows me to rule out this region as well as this region. Okay, it covers the entire contour. So at every contour, I am expending only 2 times that particular contour's cost rather than the number of plans. So that is really the main idea, and there is some nice animation of how this algorithm runs that Srinivas created, but I'll not show you this. Okay, so the analysis is simple for theory, folks. There's nothing happening here, but except that I said 2, but actually because of certain technicalities, what we can show is that in every contour we actually execute at most 3 plans. Okay, so that's why in the special case of 2 thing, you will get an MSO guarantee of 10, and if you have D predicates, what you will get is D square plus 3D, because what we can show is that although while making progress you will only execute 2, but you may have certain the same contour you may revisit in the multidimensional case. So because of that you incur another multiplicative factor, so you get D square plus 3D. Okay. So from a bounds point of view, these two are somewhat comparable, although there are many instances where the SpillBound, which is the new algorithm, does much better. But if you look at the empirical result, huge gains. Okay, so huge gains over PlanBouquet, and we have also done certain wall clock experiments I will not talk about, but we get a big boost in the worst case thing. But the problem of the compilation time thing still exists, okay, as of this. And then we also showed that no deterministic algorithm can achieve a ratio better than D. Okay, and this I am again glossing over a lot of technical points here, but the main idea here was to construct a particular ESS and specifically show existence of D query points which are all symmetric with selectivity 1 at all dimensions other than one of the locations where it is 1 over D. And you can actually show that if a deterministic algorithm actually is capable of distinguishing which of the instances you have from Q1 to QD, right, it must actually incur a cost of D. Okay, and while satisfying all the PCM assumptions, we can actually construct an instance where for each point the optimal plan has only cost 1. Okay, I am not getting into the detail of this, but again there is nothing here which surprises a theory audience, but except that there is a lower bound for deterministic algorithms, and this technique actually critically uses deterministic behavior. So for randomized algorithms we have no lower bound for what is possible, etc. This I will skip. Okay, so this is important. So dealing with compilation errors. So what I'll just, because why this is important is the reason I showed you experimental results, they had only 5 dimensions, because if you go to 9 dimensions, it actually requires you to call the optimizer almost 500 billion times. Okay, so even compilation phase becomes infeasible. So we wanted to actually address this issue, and without going into much details, what I can tell you is that Now, given any query, even if it has really large number of dimensions, our compilation phase actually is less than a minute, which means that you give me a query, I will spend no more than a minute to produce the bouquet of plans which I am going to search over. And then you know, in terms of worst case optimality, I still retain the same kind of behavior as what SpillBound gave us, which was in the region of tens, right? I mean suboptimality of 15, 20 and 25 empirically. So, you know, so we are at a stage now where for any query, ad hoc queries also, we can actually employ this machinery, right? So currently the idea is to see if we can use machine learning to see if an instance requires this kind of a robust approach, or current estimates are good enough for you to just execute the as is optimizer. Okay, that's it.